Again, this is Unit 5E. We're looking at correlation and causality. So we'll be looking at what are called scatter plots in this, which is going to come from sets of data. And we're also going to be talking about different types of correlation: positive, negative, no correlation. And one thing that we need to be careful about in here is correlation and causation. They're not necessarily one and the same. So if we look at this first paragraph here, we got a major goal of many statistical studies is to determine whether one factor causes another. For example, does smoking cause lung cancer? So in this unit, we're going to discuss how statistics can be used to search for correlations that might suggest a cause and effect relationship. So the correlation, it may suggest a cause and effect relationship, but we'll notice that when we explore this, it is a pretty difficult task to establish causality. And so when we talk about this idea of correlation, okay, there's a correlation that exists between two variables. So we're going to be looking at two different things. When higher values of one variable are consistently associated with higher values of another variable. So higher values go with higher values, or when higher values of one variable consistently are associated with lower values of another variable. Wow, I am having a hard time today. Variable. So basically what we mean is one variable increases, the other variable increases, or as one variable increases, the other variable decreases. And that's what we're going to be looking at in establishing correlation. So one example may be, the temperature outside and altitude. So as you increase your temperature, as you increase your altitude, it is very likely that your temperature will decrease. That's what a lot of people like to do in the summertime, is get up into the mountains where it is cooler. So there is a correlation between your altitude and the temperature. And we'll talk about whether that is a positive, negative, or negative correlation. Now here's a couple other examples of correlation. So height and weight for people. There is a trend that the taller the person is, the more weight they'll have, so they'll weigh more than a shorter person. That's just, it's not always a given, but there's definitely a correlation when you look at those two variables, height and weight. There's a correlation between demand for apples and price for apples. Okay, if there's more demand for the apples, then the price of the apples is going to go up. If that demand decreases, the price will usually decrease with it. Correlation between practice time and skill among piano players. So usually the more practice someone puts in, the more likely they are to be skilled. But again, the thing we want to really try and highlight here at the beginning is establishing a correlation between two variables does not mean that a change in one variable causes a change in the other variable. Okay, we notice patterns in correlation, but that pattern doesn't necessarily mean a cause all the time. Determining a cause, it takes much more work and isn't always foolproof. So there's correlation between smoking and lung cancer. So the correlation between the two, smoking and lung cancer, did not by itself prove that smoking causes lung cancer. There were other factors in there, and they had to go through a lot of rigorous studies to actually find that causation. But with lung cancer, we can imagine, there could be some gene that predisposes a person to both smoking and to lung cancer, or to just lung cancer. Nevertheless, identifying the correlation is a crucial first step in learning that, like in this case, smoking causes lung cancer. So if you're trying to find causation, looking for correlations first is a very necessary part of that research. So I mentioned earlier we're going to talk about what's called a scatter plot. And a scatter plot is just a graph in which each point represents the value of two variables. So there are going to be points on the graph, and each point is going to represent where kind of two variables come together. So here we have the biggest movies, and this is through 2016, as far as production costs. So we can see, for example, Pirates of the Caribbean, Stranger Tides in 2011, production cost was $378 million. The amount of gross receipts was $241 million. Contrast that with Star Wars Episode 7, $306 million to produce, $937 million in gross receipts. So if you notice, coming down here, so here's Star Wars right here. So Star Wars, we came across to, it was about $306 million to produce this film, and about $937 million. So they come together at this point on our scatter plot. Pirates of the Caribbean, however, it took $378 million, but they only brought in, what was it, $241 million. So they're way down here. And so we do that with all of these different movies here, and we get this scatter plot, and it helps us see quickly what that data looks like from a visual standpoint. And from here, we can look to see if there's any correlation. If there's positive correlation, you would usually be able to find a nice line that comes through at some positive slope that matches up with the data quite well. If there's a negative correlation, you would find some kind of negative line that matches up quite well with the data. But in this case, it's kind of hard to see if there is any correlation. So when we look carefully at that scatter plot of the movies and their cost and how much they brought in, there really isn't an apparent correlation. The dots don't seem to follow a particular pattern. And so we would say for the videos, there'd be little to no correlation between the amount of money that they spent producing the film and the amount of money it earned in gross receipts, or basically how much money it brought in. Now we're going to look at a couple of different scatter plots and find positive and negative correlations here. So if we look at this first one, this is diamond weights and prices. So we have the weights and the price, and notice that they have an upward trend. So if I were to draw, and that's not going to be straight for a sec, but if I were to draw a line, something like this, approximately, notice that that is the trend that they tend to follow. It's not perfect, obviously, those dots aren't all on the line, but that's a trend. It's following an upward trend. So we would just say kind of as weight increases, price also increases. That is what we call a positive correlation. Okay, so positive correlation is if that trend line has a positive slope, or as one variable increases, the other increases. And the strength of that correlation depends on how tight these points are around our line. So there's a pretty strong correlation on the weight of diamonds and the price for that. Now this next graph on the right hand side, we're looking at life expectancy and infant mortality rates. And notice, even though they're quite scattered, we do take on this downward trend. And so as life expectancy increases on the x-axis, okay, the infant mortality rate, so I'm going to put the infant mortality rate decreases. So that when one variable is increasing and it's offset by the other variable decreasing, that is what we call a negative correlation. This correlation is not as strong. The negative correlation is strong because we have some who are quite a significant ways off from our trend line, although that's not a perfect trend line at all. But that's the idea. Again, the closer those points cluster towards that trend line, the more positive or more negative the correlation. We say strong positive or strong negative. And then you can also go weak positive and weak negative. But here's again just briefly the positive, negative, and no correlation. So there's those three right there. And then a little bit about strength of correlation. The more closely two variables follow the general trend, the stronger the correlation, whether it be positive or negative. There's a perfect correlation if all the data points lay on a straight line. Now, there's some possible explanations for correlation that we can look at. One is just it's coincidental. And in those cases, it's hard to explain. It's just kind of coincidence. It just happens. Happenstance that way. Another case is both variables might be directly influenced by some common underlying cause. So one doesn't necessarily affect the other, but there's some underlying something that has a tendency to affect both variables. And then lastly, one of the variables correlated may actually cause the other. But remember, note that even in this case, it may be only one of several causes. As we mentioned in the smoking and lung cancer. Smoking, they have shown, does cause lung cancer, but there are other variables that can cause those things. That can cause lung cancer, not just solely smoking. So there could be other causes. Here are some of the guidelines in order to establish causality. So if you suspect that a particular variable is causing some effect, first what you want to do is you want to look for situations in which the effect is correlated with the suspected cause, even while other factors are varying. And then second, among groups that differ only in the presence or absence of the suspected cause, check that the effect is similarly present or absent. 3, we're going to look for evidence that larger amounts of the suspected cause produce larger amounts of the effect. So again, in the beginning, we're looking at evidence. We're looking among groups. We're just observing, gathering a little bit. And then number 4, if we're continuing here, if the effect might be produced by other potential causes besides the suspected cause, make sure that the effect still remains after accounting for these other potential causes. So if you introduce other variables and it's still present, okay, then we want to continue in here. Then if it's possible, now we want to actually get in, we want to test the suspected cause. We want to get down into the scientific level with the experiment and see if we can, if it can't be performed on humans for ethical reasons. A lot of people do it on animals. Mice and rats tend to be ones that they use, or to test drugs and other certain things, or computer modeling for other things is up and coming pretty big. And then lastly, try to determine the physical mechanism by which the suspected cause produces the effect. Try and get down into the small level as you can and figure out exactly how is this suspected cause actually producing that effect. So as you can see, causality is a pretty complex setup, and takes a lot of time. But in the beginning, we're looking at observation, and then as we get closer to the end of trying to establish that causality, we're actually beginning to test things and really try and get hard data. So that's a look at kind of part 1, a lot of general things to look at there. We'll do some examples in part 2.